All right, so now we will find the total distance from 0 to pi. So that's going to be the integral of the magnitude of the velocity vector. So remember, to get the magnitude of the velocity vector, I need to do the square root of vx squared plus vy squared. So that's going to equal the integral, in this case, from 0 to pi of, so anytime you have this magnitude, you're going to have the big old square rooty thing and a Pythagoras theorem to do. So I put in the vx, so that is 2 cosine of 2t squared plus vy squared, so that's negative sine of t squared, and that's all dt, right? So what you're seeing here is this is vx and this is vy, because the magnitude of v is equal to the square root of vx squared plus vy squared. All right, so that's what we put in there. All right, so what is that? Well, as it happens, I still have the speed function right here in my calculator as y1. I still have it there. So why don't I just go math 9 for an integral, and then go 0 to pi, yeah, and then of y1. So variables, y variables function y1. We will do dx, even though it's really dt, and I get, it's thinking, geez, you made me do a really hard problem. 4.714. Okay, 4.714. All right, so what does this mean? What that means is, from 0 to pi, my displacement is just -2 down, right? 0 is the vector. My displacement is a vector, 0, -2. All right, but what I did to get there was I went around and around and around. All right, and this distance is 4.714. All right, now, does it make sense that that distance is 4.714? You know, I recall that last week we found the total length of this thing. The whole length would be 0 to 2 pi instead of 0 to pi. What did we get when we did that? We'll flip back a little ways. Flip back through memory lane. There. So we're going to go back. We're going to go back. We're going to go back. Here, look. When we did the length of this curve, find the length of the curve from 0 to 2 pi, we used this formula, and we got 9.429. What happens if I take this number and double it? It's going to be 9.428. So the difference is a rounding error. All right, so then that makes sense that this would be half of the length, right? That's half of the length of the entire curve. That's the distance we went, all right? So that's the difference between distance and displacement. Notice distance is a number and displacement is a vector. So in a sense, distance is actually something you've already done before. It's the same as arc length for a real valued function. So arc length, you have s equals integral from a to b of square root of dx dt squared plus dy dt squared dt. And look how that's the exact same thing, because this vx is really vx squared, vy squared, and vx is the derivative of the position function. So this is the derivative of the x coordinate. And this is the derivative of the y coordinate. So vx squared vy squared is really dx dt squared dy dt squared. It's the same formula. So distance, in a way, is something you already knew how to do, which is arc length, but just changing the vocabulary to be a vector valued function instead of a parametric function. This was for a parametric function. However, displacement is actually something completely different, because now the displacement is not a real number, it's a vector. So yeah, there you go. Displacement, how far did we go and in what direction? Distance, how much distance did we cover to get there? All right, next up we'll do some homework examples.